So let's continue looking at the commands that are available. In addition to the ones that we've shown you, including date, etc., there are a few other critical commands, including the job control set of commands. Job control is the ability to send jobs to and from the background, so in between background and foreground, and the ability to control those jobs. There are commands that certainly allow us to control jobs that are running. First and foremost, we need a job that's of significant length. Most Unix and Linux utilities are small. They're designed to execute quickly, unless of course we're processing large files. And as a result, there isn't much opportunity unless, again, you're processing large I/O or perhaps extensive network I/O, much opportunity to control jobs to and from the background and foreground. There is a command that we want to throw in there called sequence, SEQ. Sequence by default, if given a number, let's say 50, will display, to stand it out, all integers, as you see here, from 1, as 1 being the index, 1 through 50. Sequence is a great way to construct loops within the bash environment. So when you see we look at looping, for example, it's a great nifty way to generate from a beginning number to a destination number, or from source to destination, or beginning to end. So sequence is yet another command, and we can specify the root or the seed. Instead of being 1, we can make it 0 and perhaps go up to 9, for example, and that outputs all of the integers that are base 10, 0 through 9, all 10 integers. So we can control the seed as well as the destination. Or if we just specify a boundary or a limit, a ceiling, it's seeded at 1 and it goes up to that particular number. So in this case, 1 through 9, 1 through the ceiling. So sequence is a great little tool, and what's critical about sequence is it allows us to generate test files, dummy files. So we can generate pretty large I/O files in addition to creating integers for us to iterate through. In the case of constructing loops within a bash environment, we can create large files relatively quickly to illustrate job control. Let's show you how that would work. First and foremost, you should ensure that you have enough disk storage space. In our case, we have a partition with 2.3 gigs. That's the default root partition. It should suffice. If we're to do sequence, for example, up to 10,000, it would display to the screen all numbers up to, in this case I did 1,000. It would send to the screen all numbers up to 10,000. But if we're to send these values, these records, to a file, the file would contain 10,000 records, or 10,000 lines. So let's show you that using redirection. We'll sequence 10,000, we'll send it to a file. We'll call this file junk1.data. It takes just the amount of time, and now when we look at the file, junk1.data, it's approximately 50K. Now this is not a good enough test for us to illustrate job control, so let's show you a more meaningful example. How about if we use a sequence command, seed it again at 1, but to count, instead of up to 10,000 and 100,000 or a million, how about up to 10 million? This will take a while, even on a fast system. Now we can show you job control, providing there's enough time if our system doesn't feel happy and create the file quick enough. Now to send a job to the background, we can use Control-Z. That sends a job to the background. It's been stopped, and if we'd like the job to be returned to the foreground, we can do foreground, FG, and the job comes back to the foreground. So again, Control-Z sends a job to the background. We can then use the jobs command to list whether or not the state is stopped. In this case, it's stopped because we executed the job using Control-Z. We have a job in the background using Control-Z, and it's been stopped. We can bring to the foreground this particular job. If you'd like to explore other options that foreground or the foreground command allows, do a man FG or an FG-help, etc. You'll see that we can alternate to and from background, foreground. Now, FG is a built-in bash shell command. Again, the jobs command also accepts parameters such as V for verbose. The jobs command will list all jobs that are running. We can bring to the foreground the job it continues running. Control Z sends it to the background. Foreground, and then you can kill it in the foreground using Control C. If we now execute jobs, the job is gone. How about if we were to run the same job, but to send it into the background while it's still processing? Before we do so, let's do an LSL on junk1.text or .data to see how far or how much it's grown. And this file is about 47 megs. We can list it using the human readable option, and it's 45 megs. Let's remove rf junk1.data, and we'll rerun the job. If you'd like to send a job to the background but have it continue running, instead of actually using Control Z after having executed the job in the foreground, send the job to the background using the ampersand. Now the ampersand can be juxtaposed with no spaces to the command, or there can be a space. Either or is fine. If we execute the command this way, in Unix, in Linux, it goes to the background, but it is executing. If we list jobs, as you can see, the status has changed from stop to running. If we LSL H, or LSL so we can see the bytes, junk1.data, we can see the file growing. We can in fact watch the file grow using watch LSL junk1.data. And we'll just see the file being created here. It's up to approximately 55 megs, and it's growing, writing 10 million records. Excellent. So while this is writing, we can control the jobs, as I've mentioned, using background, foreground. Jobs will list it. We can bring it to the foreground. It's the only job. Now, if there were multiple jobs, we could simply do a control or an FG with the actual integer. Now I've actually stopped the job. And if we bring it to the foreground, it continues running, creating the file. So that's a little bit about job control. Jobs, background, foreground. There's some other neat commands such as sort, unique. Let's actually remove junk1.data. Sort, unique, for example. In order to illustrate how sort and unique works, we need to create a dummy file. So let's create a new junk1.data, and we'll place some values in it. We should put them purposely out of order. So, for example, let's say on the first line we'll put the number 2, the second line the number 1, and on the third line we'll put Linux CBT, and the final line, or the next line, we'll put Debian. Final line we'll put Red Hat. So we have some values, some simple values. We can cat junk1.data. It's very basic. Let's sort junk1.data. Notice how the values have been altered. 1 is now first, of course, logically. 2, Debian, Red Hat, etc. Or Debian, Linux, CBT, Red Hat. So sort will, by default, sort whatever you pass into it, whether it's sent via pipe or passed in on standard in, the values of the given file. Sort also has parameters that you can consult for additional help in the different ways you can actually sort the file, whether or not you want to merge, ignore the case. Oftentimes you want to ignore the case, perhaps do a numerical sort, etc. So that's something to consider. There's also the unique command. Now let's modify junk1.data and create a situation where we have two records that are actually the same. Let's create another Debian entry, and when we operate on this file with sort, it'll sort it, it'll list the same values twice, but often in scripts you'll see sort executed on a file and then redirected using a pipe or piped into the unique command. The unique command will then eliminate duplicates. In this case, the output is now nice and clean. The duplicates are gone. Excellent. So that's a little bit about sort and unique. You can which sort, it's in bin. Which unique, it's in user bin. Two other useful commands that you can use in your script to alter the appearance of your data. Now there's another neat command, the cut command. The cut command will allow us to specify a delimiter and extract the fields that we're interested in. So many text files within the Linux environment is delimited by some sort of delimiter. Most often you'll find that files are delimited by space. Sometimes you'll find that files are delimited by other delimiters such as comma or colon or semicolon, etc. A classic example of a file that uses a non-standard delimiter, non-standard in Linux meaning non-space, is etc password. we can cat etc password. It contains multiple values, and these values, these fields, are delimited by the colon. So what if we want to use the cut command to extract perhaps the second column, which contains a reference to the shadow file? Well, we can cat etc password, which dumps the file as you see it there, but then pipe the output into the cut command, specify the field as well as the delimiter. Order isn't important, so we'll specify the delimiter in this case as colon, and the field that we're interested in is number 2. This will return all X's. It's not much help, but we were able to extract that particular field. How about field 3? There's field 3, which corresponds to the user ID on the system. Of course, user ID being user ID 0, the very first user ID created when we install the Linux system, regardless of Linux flavor, belongs to root. We can cut field 1, you'll see the username. Now how about cutting multiple fields? Similar to awk, separate the fields by commas and you'll get those particular fields that you're interested in. And we'll just get here 1, 2, and it brings 1, 2. Doesn't need to be in order. We can get fields 1, 4, 7, and there you have it. So cut is another useful command. Another useful command is the character translation command, the TR command. Very useful. It allows us to operate on characters. Let's show you some examples. First, do a which TR, and you see it's located in user bin. TR help returns the options that the character translator will accept. Aren't too many options, but it is very useful. The 3 main functions are as follows. We can complement, which allows us to do a negation test. We can delete characters, and we can also squeeze repeats. So wherever we find repeats, like how we just had Debian, for example, we can perform a similar function. Now the other, of course, option is substitution. Substitution is mainly what you use the character translator for, but that's implied by default. So outside of substitution, you have the complement, delete, and squeeze abilities. Let's show you how you use the translate command. You're going to specify you're going to send some, so we're going to send some data into, using a pipe initially, into the translate command, and then we'll have it operate on the first set, which is the rule we want it to follow, or the rule that we want it to match, applied to the second set, which is the rule that we want it to follow. So let's echo, for example, some text, file 1, which is all caps, and we'll pipe it into the translation command, and we'll say wherever we find uppercase A through Z, in other words, all alpha characters uppercase, replace it with lowercase a through Z. Now file 1 has been converted to lowercase file. Of course, the integers or the numerics are of no case, but the word file certainly is. So here's a simple translation. We've sent a string of text into the translation's input stream, and we've converted from uppercase to lowercase. Now we can use the POSIX standard way of specifying upper and lower by using the classes you see here. So in set 1, we'd specify, for example, wherever you find upper, in set 2, replace it with lower. And there are also other character classes for different types of characters, blanks, control sequences, etc. The translation tool is able to read those different characters. So the basic way you use translate and the way you would use it in your script is as follows. Translate, specify an option, whether you want to squeeze repeats, delete, complement, etc. And you specify your 2 sets. Set 1 contains the set that you're searching for. Set 2 contains the new mask or the new rules, the way you want to translate it. So let's look at some other ways we can use translate. Now if we had, for example, a string with multiple characters of the same, for example, let's say file EE1 will translate all uppercase characters, in this case, but we're going to specify the -s option to squeeze repeats. This tells translate to find the repeats, and now it echoes a nice clean file 1. Now you may be wondering, what about also changing to lowercase as we originally did the string file 1 that we piped into the translation tool? Well, simply repipe the output back into the translation command and specify the options we did before, such as uppercase A through Z becomes lowercase a through Z, and it works nicely. Again, we can also use the POSIX character class by doing the following. We'll say wherever you find upper, change it to lower. And there should be a space between set 1 and set 2. We'll change it to lower, and now it becomes lower. So you can use either way. Just do tr help. No need to remember them. There's absolutely no need. The man pages are excellent enough. Our role is to simply point out all of these useful utilities on the system so that it makes your life much easier when you need to consider how to perform these functions from a shell script, considering that unlike the other scripting languages that we show you, such as PHP, Python, and Perl, Bash does not have these functions built in by default. So there aren't modules that Bash can call upon, but there are utilities on the system, such as tr, sort, unique, cut, etc., that we can consult to get the job done for us. A common usage for translation is with regards to or with respect to file names. So for example, you'll commonly find scripts that actually translates, let's say, uppercase or lowercase file names to another case. Now we're going to show you a quick example of that, although we've yet to go into loops, etc. And before we do that, there are other options. Again, as I mentioned before, we can squeeze repeats, we can complement. So in other words, whatever match that we place within set 1, ignore it. Just operate on all characters that don't match set 1. So for example, we have this file 1 stream. Let's mix it up a little bit. We'll specify file 1, uppercase E, uppercase F. And we're going to send this into the translation tool. Now let's say, for example, we wanted to complement the classes. In other words, don't operate on the classes A through Z uppercase. So let's say we didn't want to operate on A through Z uppercase. That would correspond here to F and E. Then we could specify here uppercase A through Z becomes A through Z, and it would be ignored. So as you see here, it specifies the Z. In this case, it actually replaced it with the Z. So in other words, it operated on the characters using the C option that we told it to ignore. So we replaced it with Z, and it just ignored the characters that were actually uppercase. So it operated, in fact, on the lowercase as well as on the numeric. So you can use the -C option to negate or to ignore some of the characters that you are interested or you're not interested in matching. Now how about actually looking at the file name example? Let's make a directory here. We'll call it temp2a, and we'll work within temp2a. We'll create a script. We'll call it tr1.shell, and this particular script is going to contain a quick loop, a small loop, but we need to specify a shebang header which points to bash, and standard author, date, and purpose. Simple script, just to illustrate a point, although we've yet to go into many of these subjects. And the purpose is to illustrate using tr in a script to convert upper to lower file names. So that's our description of the script. How do we go about constructing a script that actually works? Well, first we need to set up a loop. So let's loop through the list of files in the directory. And in order to do so, we'll simply use a for loop, and we'll define a variable called I as our index, which will house each element of the list that's returned. Since for loops within the bash shell environment function as iterators through lists. So for I in, and we'll use command substitution here, ls-a to get the list of files from the directory. We'll then do the following, and when we're finished, we'll be done. So in the body, we're going to do what we want to do. In the body, we're going to set a new name that we'd like the file to be called. So we'll say new name. We'll set a variable. New name is equal to, and we'll echo I, which contains a current file name, and we'll pipe that into translate. Now we don't always have to pipe into translate. Translate can actually read from standard in or from a file name if we use the redirection character, the inbound redirection character for standard in. So we'll translate A through Z uppercase to A through Z lowercase. So new name will contain this value as per the rules of command substitution. And then we'll move I, which is still the uppercase version or uppercase name of the file, we'll move I over to new name. Now in order for this to work, we need to ensure that the files that are in the directory are uppercase, or at least there are some files in the directory that are uppercase. Let's save the script and we'll Control-Shift-T to open a new window. We'll navigate into temp2 then temp2a. Now we have the script, but we don't have any files to operate on. So let's create a file. We'll create several files using Bash's abilities. We'll call them file, and we'll use brace substitution, file 1 through 5. So now we have 5 files. They're all uppercase, and we can attempt to run tr1.sh, and it will ascertain or create its list based on these files that we see here. And one by one, using the iterator, the for loop iterator, it'll store each element. So, for example, the first element, file 1, will be housed temporarily in the variable I. We will then operate on I. We'll create a new variable called new name. We'll echo I, which stores the name, not necessarily the contents of the file, not the contents of the file, but the name. It'll echo the name of the file into the character translation utility. The character translation utility will search for, within the string, cases of uppercase characters and translate them or render them to lowercase characters into this new variable called new name. We'll then use the move command to move all of the original names over to new name. So it's quite simple. Let's try to run this script. And let's do an LSL. Now in this case, what it attempted to do was, of course, to move our script. We didn't put any exceptions in there, such as if the current value of I is equivalent to script name. We certainly could have done that. So for example, we could have said if I is equal to, using our comparison operators, if I is equal to $0, which is the name of the script, then ignore it. Otherwise, continue. That's certainly an option. So again, we've now converted files 1 through 5, which were originally uppercase, to lowercase, and we could go in the reverse fashion, which would also affect the script, which is why we should put a condition in there so that it ignores it. So for example, we could say go from lowercase a through z to uppercase a through z, but you don't want to harm the script, so we should put a logic or some sort of logic in here which says if I is equal to the current name of a script. Now to get the current name of the script, you could just simply echo it, and let's just do it. We'll echo 0, and then we'll exit the script so that we don't perform any operations. Let's run the script, and the name of the script, well, it's exited, so let's flag it executable so that we don't run into that problem. It exited because it ran within the default bash environment. So let's change mod u+x, the script that's in this directory, and now we can execute the script directly. So this is the name of the script, but if we're comparing within a loop, we should use base name, for example, because base name will strip the directory name. So we'll echo 0, but really what we should be echoing is the base name of 0, so that we don't get the leading directory. Let's try it again. So here's the actual name. So now stored in some sort of variable, such as my script name is equal to base name 0. Now within our loop we can say if the element of I is equal to our name, then ignore it. So for example, we could say if I is equal to, and in this case it'll be equal to my script name. There will only be one instance where it is. Then we'll do nothing else. And we could even echo here. Go. Sorry, can't rename myself. and then we'll move on, else if, and then we move on to the rest of it. We can just put an else statement if it's just one case, or if we don't want to run into any issues, or else if I is not equal to my script name. And this is the long way of doing it, but then we do the rest of the logic you see here. Let's just bring this in, and we need to close the if altogether. So let's take a quick look at this. So we're testing whether or not I is equal to my script name. If it is equal to my script name, then echo sorry, can't rename myself. Else, if it's not equal to my script name, then we perform the assignment of the new name, and we move, etc. Now we can change our translation from uppercase to lowercase a through z to move it back to uppercase a through z, and then we need to close the command substitution. Now let's go back to the shell, and barring no explosions, we should be okay. And in this case, the script is actually exiting before it gets to do the work, because we didn't comment exit out. So let's comment out exit. Let's try it again. And there you have it. So it says, sorry, can't rename myself, and it's renamed file1, but it hasn't touched ourselves. So that's quite simple. So we'll be looking at some other basic things you can do with the shell.